Okay, clearly this ain't going to work with the code we have so far. So we're going to overcome the problem that this monstrosity of a thing can't be broken down easily using recursion. Specifically, what we're doing is going to break down this whole thing into smaller instances of the same structure as the original. Specifically, let's look at what we're working with. So it's a nested list, right? And a nested list can be broken down into smaller instances of the same thing. So we want a structure that can deal with the possibility of a list, of a list, of a list, of a list, so on, of lists. So a nested list, the way we're going to call it, has two possibilities. Either it's just going to have a number in it, which is not really a nested list, it's just a list, but, for the sake of our structure, either it's going to have a single number in it, or it's going to be a list of other things, other nested lists. And each of these sublists is called a subnested list of the original one. So this is a recursive definition. Nested lists here are defined in terms of other nested lists. So a nested list could be nested lists. It sounds like so repetitive, right? Another word for recursive definition, by the way, is self-referential definition. Random aside. Now, it may seem weird to suggest that a single integer is a nested list. For instance, if you did isInstance3 list, it's clearly not. However, we're going to do this for convenience's sake, because when it comes to a recursive definition, it makes it a lot more elegant for the code that we're going to write to solve this problem. Now, the depth of a nested list is the maximum number of times a list is inside another list. So the depth of a single integer is 0. So this has a depth of 1, the list that's 1, 2, 3. And this, the 1, 2, 3, 4, 5, 6, 7, 8 with a bunch of lists in here has depth of 3. And the reason you can see that is you can see goes in 1 step, 2 steps, 3 steps. So this is the quote unquote deepest that we get. This is an exercise, try to figure out how deep this one is. Here's a hint, consider counting some of the arrows. Now, we can use this definition to guide the design of a function that computes the sum on a nested list of numbers. So, here is our new way of summing things. Sum nested, which takes either a integer or a list. If what we have is an integer, to sum it, you just return it. That seems pretty simple. If it's not an integer, that means it is a list of nested lists. In this case, when I say nested lists, I mean it could contain a bunch of numbers, it could contain lists of a bunch of numbers, or lists of other lists. The sum starts out as 0. For each of these sublists in the object we're working with, we call this function again and return our summation. So this is our first example of a recursive function. And the reason you know it's recursive just by looking at the code is you see here is a function name. It's calling itself inside of the code. So just like we defined a recursive data structure that is the nested lists to refer to themselves, we're now defining a recursive function that operates on these nested lists. Now, notice here, once again, kind of the structure of how the data is represented in the structure of the code. Just like a nested list separates the possibility of you either have an integer or you have some lists, the code exactly has an if statement to represent that. And like our recursive definition of a nested list mentions that a nested list can contain nested lists, our code also has a loop over this call to itself. And sublist here specifically are the internal lists of our original outer one. So something to note here, and that you'll see among pretty much all recursive algorithms you run into, is this little block at the top where you originally have a very simple case that could happen immediately with a return statement. And this is what we call the base case of the code. In other words, anytime you have sort of the simplest form of the object that you're working with, you should be able to do something very trivial to return the answer. So in this case where we're summing up numbers, if you have a number, well, the sum of a number is itself, so you can just return that number. Not a lot of work needs to go on here, but this is super critical to make sure that your code won't just loop on forever. You need to have an exit strategy, or in this case, a base case. The other scenario where it's not a number and is a list of stuff is what we call the recursive case. So solving this problem requires you to break down whatever input you have into something smaller, whether it's numbers or smaller forms of lists, and calling your recursive function to continue to break things down step by step. So this example is kind of the simplest kind of recursive function you're going to see. It just has one base case, one recursive case. Later on, we'll look at more complex data structures and functions where you might have multiple base cases or multiple recursive cases. Now, with regards to reasoning about these recursive calls, we say that the call to sum nested inside the for loop is a recursive function call because the call to sum nested is inside the function that's also called sum nested. So these function calls are handled the exact same way any other one is, but because of the way recursion works, it's possible that a single function call might resolve in a bunch of different calls to that same function over and over again. And we can probably take a look at this in a little bit, exactly how that appears in our stack frames. When given a function call on a really complicated nested list, you might be tempted to trace through the code carefully, looking at what happens on each recursive call. So your thoughts go something along the lines of, well, we enter the loop, we make a recursive call, that one will make this other recursive call, which makes this other recursive call, and so on. You can do this, and it's what a computer will do for you, but it takes a lot of time, and it's very likely you might make a mistake somewhere along the line. So instead, anytime you're given a recursive function and some input that you want to figure out what will happen, you should use a technique called partial tracing, which I'll describe for you right now. And there's two cases that you have. First, the input is a base case. So let's suppose you want to figure out what happens for sum nested 5. Well, 5 is an integer. It's the simplest kind of nested list, quote unquote, that we're working with. So this is the first if statement. So you can completely ignore everything in the else side of things, and you just say, okay, if it's a 5, return it. Oh, great, cool. That's exactly what we wanted. Sum nested list should return 5 because the sum of 5 is 5. No, okay, that's the simple side of things. Now things get trickier. Suppose we want to trace this one, the sum nested of 1, 2, 3, 4, 5, 6, 7, 8, where they're all in a bunch of lists of forms, and verify the correct output is the sum of all these, which if you can't do the math in your head quickly enough, it's 36, and you know that because you can do 1 and 8 is 9, 2 and 7 is 9, 3 and 6 is 9, 4 and 5 is 9, 9 times 4 is 36. This input is where we do the else side, right? Where we're specifically going to be looking at this. Now, this code here is something called the accumulator pattern. In other words, we are looping through the object, and for each of those, we're updating an accumulator or a sum, the variable s. Tracing this on your own is probably pretty challenging because every time we do our loop, we're making a recursive call to sum nested, which you then have to trace itself. So a key idea of partial tracing is the following. We'll trace through here, but every time we do a recursive call, instead of like quote unquote stepping in and seeing what happens through here, we'll just assume that it works and just use the correct return value and trace the rest of the code. In PyCharm, if you're using the debugger, this is like using step over instead of step into when you reach the function call. So to facilitate this, we'll use a table of values and we're going to build it up. So first off, we take our input object, which is the list of 1 to 8 of various lists inside, and identify all the sub-nested lists. So now there's only 4 of them here. You can see we got 1, then we got the list with the 2, 3, 4, and 5, then we got 6, 7, and then we got 8. So here are the 4 actual elements of our original list. Now beside each one of these, you can write down what sum nested should return on the input. Remember, we're not going to trace anything here. We're filling this in based on the assumption that the documentation here, which is, where did I put it? Return the sum of the numbers in the nested list, assuming that that is correct. If it is correct, then what should we get? Well, the sum of 1 should be 1. Assuming that our code is correct, the sum of 2, 3, 4, 5 should be 14. Assuming our code is correct, the sum of 6, 7 should be 13. The sum of 8, we can pretty clearly see, is going to be 8. Okay, cool. Now, we'll trace through the code from the original else block, updating the value of the accumulator using this table, and we can show these results. So the first time we go through, we got the sum of 1, it's 1, so now our sum is 1. Then we're going to do our sum nested on the 2, 3, 4, 5. The answer we should get is 14, so our sum should now be 15. If we do it on 6, 7, the sum we should get is 13, so our sum should go from 15 to 28. Lastly, our sum is 8. We figure 8 is the sum of 8, and 8 plus 28 is 36. Hooray! We have reached the value that we expected to get from our original call to sum nested. So, this probably raises some suspicious red flags in your mind right now. What do you mean you assume that the calls are correct? What if they're not, right? In other words, yeah, cool, this is like a simple technique, but why should you trust that it's just gonna work? Turns out that you can do so provided the following is true. A, your base case must be correct. If there is any problem with your base case, this whole thing goes out the window. And for this, because the base cases are usually pretty simple, you can trace the code to make sure that they are correct. Secondly, every time there is a recursive call, you must ensure it is on a strictly smaller input than the original input. If you are recursing, say, on a nested list, a smaller one is one that has less depth. Because we're going through the elements of the original list every time, you're guaranteed that that's going to be the case, so everything is cool. However, if we weren't doing so, if we were doing, and so you can see, let's go back to our code. When we do sum nested, if we were doing it on the original object and not on the sublist, this would just loop forever, right? It would continually do the same thing over and over again. It's important here that the call we're making with the recursive function is to a strictly smaller size input. That way we can ensure at some point it will eventually reach our base case, and that's the reason that this is going to work out. So here's how to apply these ideas to show that our code is correct. Since I'm confident that the base case for sum nested works, I now know that for any list of depth 0, sum nested works. So in other words, anytime you just give it a number, it should give you the number. If you have a nested list of depth 1, then your recursive calls are going to be on nested list of depth 0. We know that those are going to work because we just said so. So based on our partial tracing, we know that sum nested should work for any list of depth 1. Okay, now what about depth 2? Well, every recursive call you make there is going to be on a nested list of two possibilities. Either it'll be depth 0, which we already know works from the first thing we said, or depth 1. Well, we just figured out that if it's depth 1, it should work okay. So that means that both of these possibilities, depth 0 or 1, should work all right. Since they're working all right, sum nested is correct for depth 2, and so on and so forth. This is formalized in the principle of mathematical induction, which is a formal proof technique you'll learn in a bunch of other courses. CS165 it says here, pretty sure Math 102 covers it. You'll definitely see it in CSC148, especially if you have me for that course. And so we're not going to go over induction in detail here, but it is really the basis for why recursion works the way that it does. Now, what does this mean for, testing things and debugging and so on? So, flip side of this is if you have a recursive function and it's wrong, so you fail a test case that you wrote, there is only 3 possibilities for why that happened. Number 1, base case is wrong. Should be pretty quick to see that. Number 2, one of or more of the recursive calls, remember it's possible to have more than just one recursive call, is not actually made on a smaller input. It's made on something either bigger or the same size, which means it's not guaranteed to actually stop. Or 3, the recursive case is incorrect even if you assume all the recursive calls are correct. In other words, it's not the call that's the problem, it's everything surrounding it that has an issue. Maybe you didn't initialize your accumulator to be 0. It started out as 1, for example. So there is a good old design recipe you can follow if you're going to be building your own recursive functions. First, identify the recursive structure of the problem. In other words, what is the way that the input refers to itself in some way or form? Does that mean it's a nested list, which can contain nested lists? Or is it some other kind of data type that can be expressed recursively? In other words, expressed in terms of itself. Once you have done this, you can usually write down a code template to guide the structure of your code. And for example, for nested lists, it might look something like this. Here is our function that takes either an integer or a nested list, or a list, in other words, a nested list. If it is an integer, this is your base case. Otherwise, for each of the sublists, ensuring that we're breaking them down, we recursively call. For the second step, identify and implement what this base case should be. You can usually tell what this is like pretty quickly, which makes it not too hard. For nested lists, the common base case is, an integer, so it's pretty easy to avoid missing that here. Step 3, write a concrete example of the function call on an input that has a level of complexity. So pick a nested list of depth 3. Write down the relevant recursive function calls based on the structure of that input and what they output according to the function's docstring. In other words, write those columns down like I did earlier in the section on partial tracing. 4, take your results and figure out how to combine them to produce the output that you're looking for. This is usually the hardest thing that you need to do, but if you can do it, you can implement the recursive step pretty easily in your code.